Welcome everyone, and thank you for this opportunity. My name is Shridhar Prabhuraman. I belong to in Maritime Research Center in Pune, in India. The title of my presentation today is going to be Area Production and Yield Analysis for Integrating Mathematical Modeling in Aquaculture to Predict the Growth Dynamics for High Yield and Sustainable Operations. Now, it's a rather long title for a presentation, but throughout this, I hope to do some justice to this. At the onset, I would like to first acknowledge that the primary author for this work is my colleague and I'll be making a presentation as a co-author for this work. Right. And I'd also like to express my gratitude to everyone assembled here today for the presentation and the World Aquaculture Fisheries and Seafood Conference for giving this platform where we can collaborate and share our ideas to the world. So let's first begin by understanding what aquaculture is and its role in the seafood industry before we lead to the problem statement that we have. Now, the seafood industry is experiencing an extremely huge demand, which is much more than the anticipated level. What we had pre-COVID, it's even surpassing that. The compound annual growth rate, as predicted by the Fortune Business Insight, is around 10.14%. Right now, in 2024, we had the industry for 386 billion, and that is expected to grow to 837 billion by 2032. Now, this aquaculture is increasingly becoming the major share and the initial point for any kind of maritime product and supply chain. And as compared to the capture fisheries that we have, the aquaculture, at least the overall global production of aquaculture is much more as compared to what we have from the captured fisheries, at least talking about the shrimp production per se. Now, what this seeks for is something that we can create a model with this huge amount of numbers, with huge amount of expectations coming and growth coming in. What we actually need is a model that can go hand in hand in terms of both profitability and sustainability. So the existing challenges that we have for the aquaculture ecosystem are twofold. One is the overuse of resources. There is the point being that currently the farmers in most of the cases are making much more using much more resources to perform any kind of cultivation of shrimps or any aquaculture cultivation for that matter, and that leads to imbalance and the long-term negative impacts. And the second one being the productivity of regions, which varies with time as climate change effects are becoming more and more prevalent. Now, to establish the overuse of resources, I'm pretty sure there are many such examples. One of the examples that we did find is one where in Bangladesh, where when there was an overuse of resource for the expansion of shrimp aquaculture, this led to a lot of consequences. The groundwater salinity increased, and therefore that destructed the complete ecosystem to the point that even today that ecosystem is not being able to be revived. So then, whatever we do, whatever work that, whatever aquaculture aspect that we take into consideration, there needs to be two primary aspects that we need to fulfill in terms of the overall model that we are building. One is the profitability, and the other part is the sustainability. Profitability in the sense that as a farmer who is performing shrimp cultivation, who is getting into aquaculture, they need to have an economic gain out of the work that they do. And the same goes for the country as well, that is putting in the efforts and the resources investing in this particular industry. The second aspect is sustainability. As we have already seen, sustainability is a big factor. If we do not have sustainable practices in place, the environmental impact will lead to a long-term downtrend in the production, and therefore it will also again impact the profitability and of course the environment in general. To give an example, what I mean by sustainability and overuse of resources is if, for example, if for shrimp farm, again, this previous speaker spoke about stocking density rightly. The idea is that if you have if you cultivate too many shrimps in a single pond, the stocking density increases. When the stocking density increases, there is a reduction in the overall growth of the shrimp, and that would essentially mean that if you are if you have 100% production ratio, what we'll essentially gain is only 60% and 40% is going to waste. And when we say going to waste, these are basically nitrogens that are being thrown out in the environment. So sustainability, again, a big factor that needs to be taken into consideration. So what we propose here, the solution that we have undertaken and that we are building upon, and we also have an application around it, which I will showcase, which uses machine learning and Internet of Things to address these concerns, such that as a farmer who is getting into this project of aquaculture, they essentially have a estimate or an understanding of what are the optimal parameters that their ponds should be in real time so that they can appropriately adjust those values and for a better yield. So the research ideology as such is that aquatic species, like any other kind of living creature, living organisms, the metabolism is susceptible to environmental conditions, and that when we say environmental conditions such as the temperature, the salinity, and so on, all the environmental condition that they are present in, that affects their health, overall weight, the resistance to diseases, and so on. So what we are trying to do here is we are trying to map the relationship between these conditions and the growth rate of the organism. That is pretty much the core idea behind the research. Now, the primary subject for this research is just shrimp. So every organism has a different reaction to the environmental stimulus, and therefore the operant relationship for one organism might not be suitable for the other organism. Shrimp aquaculture is a booming industry, and therefore what we have chosen is shrimp as the subject of research. Now, even within shrimp, different shrimp types have they have different features, they have different metabolism, different this thing. What we have gone ahead with is the Vanamai as the shrimp type for our project. There are many species, but as we can see from the chart, the India's overall shrimp production, starting from year 2010 to 21, the largest is Vanamai. Today dominating to approximately 95% of the total aquaculture production in India. Um, so when we talk about, moving forward, whatever we describe is essentially for one particular shrimp type of Vanamai. Um, Now there are three different parameters that affect the growth of shrimp: the temperature, the stocking density, and the water quality. And all of these are the parameters of the pond where the cultivation happens. The temperature in degrees Celsius where it is cultivated. The stocking density, again, just to refresh, the number of shrimps that are cultivated per unit area, measured in per meter square. And the water quality. The water quality in itself includes three different aspects: the salinity in parts per trillion, the pH level, and the dissolved oxygen. The pH level basically showcasing how alkaline, etc. it is, and the dissolved oxygen level of the water, which is also extremely important. So taking all these three parameters into consideration, what we come up with, I mean, the basis of the whole research or the whole project is a function, which is to perform a mapping between all the parameters that we see, and the output being the growth rate of the shrimp. And that's essentially what we derive from a machine learning model. So a basic machine learning can be used to obtain this kind of a mapping between the input and the output parameter. So what exactly that function f is supposed to be. Uh, in this problem framework, the growth rate is the output variable, and the temperature, stocking density, pH level, salinity, and the dissolved oxygen are the input independent variables that we have for this equation. Now, um, what for simplicity of our work, what we have done is we have considered the growth rate to be constant for the complete duration of the shrimp's growth, which means that for one particular cycle of shrimp's growth in a given pond, we assume that the environmental factors such as the temperature, salinity, pressure, all of them will remain to be constant, um, and therefore that the model is thereby trained on top of that. So when I keep saying model, this essentially is nothing more than a second order polynomial regression model. Now, for the sake of simplicity, we haven't displayed a lot of equations here. But technically speaking, this essentially involves two parts. One is a growth curve and one is a scaling function. Now, the growth curve is basically the machine learning to generate a curve-fitted polynomial equation that models how the Vanamai grows at different temperatures. And we do it for three different sizes because the size of the shrimp during the growth of the shrimp, the size at which the shrimp is between the small, medium, and large as we bifurcate it, it will impact how the growth, what is the growth rate that is of the shrimp. As you might already know, the the more the size is, or the later the stage during the cultivation is, the lesser the growth rate is. It diminishes as and when we move forward. The other aspect is the scaling function. The scaling function in the sense that once we have identified what will be the growth rate with respect to the temperature, what we then do is we also look at, we scale it up or down based upon the stocking density, salinity, and pH. Because what we obtain from the temperature is an ideal value that will be there, but the other parameters could vary. So we essentially take that variation into consideration, and we what we obtain finally is a growth rate function. Right, and then, again, an integration of starting from 0 to the overall days of cultivation. Now, skipping all those equational aspects, so what I mentioned about the small, medium, and large shrimps. Um, so these three graphs showcases the variation that we obtain. For the starting from the left being the small shrimps and the right being the largest of the shrimp. Uh, our polynomial regressor essentially has it's a curve fitting across the data points that we have obtained. These data points are obtained from open source data sets and some closed source data. The curve fit showcases that how the growth rate after a certain point the growth rate starts becoming stagnant, and this is more prevalent in the larger shrimps. A smaller shrimp, for example, can take up around 30 degrees of temperature. It will be able to survive and it will still grow. However, you can see that the optimum shifts a bit towards the left when we move away towards the larger shrimps, where again the at 30 degrees or at 28 degrees, 28 degrees and so on, the growth rate decreases substantially. So this establishes that, so our model basically incorporates this into consideration that the later in the stage of cultivation, the growth rate will adjust automatically. And these three are dynamically switched in the model. Every single day we calculate what is the growth rate, and we take the input of what is the size of the shrimp and so on, and what is the overall weight of the shrimp, sorry. And we taking that into consideration, the model switches between whether the shrimp is currently small, medium, or large. And the polynomial that we have created for each of these three different uh, shrimp sizes, they basically are switched accordingly. Now, stocking density again has a substantial effect on the uh, overall shrimp growth rate. Now, as we can see the declining curve here, as you increase the stocking density, there is a decrease in the shrimp growth rate. Again, that is something that our model fits accurately, almost accurately. There are some thing, but the point is, so what we're trying to do here is sorry, what we're trying to achieve here is essentially create a model that takes all of these things into consideration and gives you one application, one model, one global model that will give you the optimum parameters. I'll show you an interface of the application that we have created for the same. Now, based on the cumulative variation with all the parameters taken into consideration, as you can see in the graph on the left-hand side, you can see that the final weight of the shrimp versus the stocking density, the optimum value here is ideally found to be 25 to 30 degrees. And we see that as you increase the stocking density, the final weight that is obtained of the shrimp keeps reducing. So for the best, so lesser stocking density is obviously good. I mean, and that's something that is theoretically as well established. The lesser the stocking density, the better it is for the shrimp, the more space it has to grow and something stuff like that. The other aspect is the temperature, stocking density, and the total biomass. The total biomass essentially is that at the end of the cultivation, the overall biomass that is present for the overall all the shrimps in the pod. Again, as we can see, the increase in the stocking density, again, the more the number of shrimps, obviously the biomass will increase, but you can see a bit of it starting to saturate, a bit of saturation happening as the stocking density leads to a certain point, and there is no net overall increase in the biomass. The temperature again remains to be the optimal one, being 25 to 30. Again, all of these are results that the model predicts in real time. Now, it cannot always be about just the environmental factors in the region. From a practical perspective, there is also an aspect of survival rate that we have taken into consideration and incorporated. With an increase in stocking density, there is definitely a decline in the overall survival rate of the shrimp. So now, taking that into consideration, we can see that given the optimal temperature as you increase the stocking density, the saturation hits much more earlier. So it's not also from a farmer's perspective. A farmer might go ahead and say that, okay, I'll have a 160 shrimps per square meter as a stocking density. Assuming in his mind, he will basically be assuming that the more the shrimps I have, the more the biomass I'll obtain, and therefore my net profit will increase. But we know that is not the case. This particular point where he should have stopped at 100, but he went up to 160. So this 100 to 160, that 60 shrimps per square kilometers is an extra excess that is going to be dumped into the water, or basically it's going to go into an environment, causing a decline in the habitat, being released as a nitrogen or any other such kind of compound that affects the environment per se. So, and even in terms of the net profit, in terms of resources that the farmer has expended, he has expended resources for 160 stocking density, but the advantage, the profit he's going to get is only for 100. So that's again. So this is the overall idea behind the work that we have, this model that we have created. And then we have validated it in two ways. One is theoretically, again, using the experimental data set that was provided by Abdul Rahman. We can see the data set provided us the weight, the survival rate, the stocking data. We calculated, we cross-verified, and we found that we have a mean error of between the actual and predicted one. The mean error in shrimp weight is around 0.5 grams, and the root mean square error is around 3.7 grams, which is, if you look at it from a practical perspective, less than 20% of errors, which is extremely operationally efficient. The other advantage of this model is essentially not being too heavy. It's not a neural network that is working behind it. It's not a random forest or any other kind of a model. It's a simple polynomial regression, polynomial curve fitting that we are performing here. And therefore, it allows us to dissolve this into more of a handheld devices into IoT without expensive calculations, while still adding some value to the farmers that are present on the ground. Now, coming to some observations, we see that shrimp show a strong variation in growth rate with varying temperature as well as stocking density. The temperature around 30 degrees were found to be optimum, and the lower stocking density favored individual shrimp growth. Of course, the higher stocking density favored the overall biomass, but to a certain point before the growth rate decline starts hitting. When you have the lowest stocking density, the overall biomass is less. The optimal pH for the growth shrimp was found to be around 7 to 9 in that space. The higher dissolved oxygen is extreme. So dissolved oxygen, again, we did not talk about this. Dissolved oxygen is also an important aspect. We saw that after dissolved oxygen, after a certain threshold, is extremely crucial for the growth of the shrimp. If your dissolved oxygen level in the pond is less than the given threshold, the shrimp growth is affected. Unfortunately, I don't remember the exact threshold value at this point. Higher stocking densities does not overall affect the farmers because of the declining survival rate, and this is something that we have seen as a mistake performed by the farmers over and over again, for where they basically feel that the more they pump into the pond for cultivation, the more profit they'll obtain from it. So the proposed solution and work we have the following advantages. I mean, in terms of the novelties and in terms of what has happened in the past and what we are doing. This current methodology is either non-existent or is very less talked about in the literature. The literature covers the impact of each individual parameters on the growth of the shrimp. For example, effect of temperature or effect of stocking density and so on. But there is no one particular model which combines all of them together and provides a real world application or real world usable model. So that's what the notion behind this work was. And of course, it also brings the machine learning and IoT into consideration. So at the end of the day, the work needs to go to the farmer. It needs to be able to applied by the farmer. Otherwise, it will be left as a research that we do. The data acquisition, again, some closed source and open source data. Okay, there are also some limitations of this current architecture that we have. Feed quality and the feed quantity affect the growth of the shrimp significantly, but we could not quantify that or incorporate that into our model because of the lack of data that we have. And again, in terms of way forward, this is one more aspect to look at, how to improve the feed quality and the feed quantity. And the work that we have done, this is again more of a proof of concept, but is essentially for the randomized shrimp category. And this is not something applicable to every family because every family, as I said, has different characteristics. Now coming to the application that we developed, again, a handheld Android application which has this model incorporated into it. as a farmer, you essentially input into it the temperature, stocking density, salinity, pH of the water, the amount of feed, and the days of cultivation, the rough days of cultivation. And what the output will essentially they give you the, I mean, the application, it will showcase you the weight curve and the growth rate curve, which tells you that how much yield and how much survival percentage has been predicted based on the parameters that you have inputted. So this is the phase one of it, wherein we provide the farmers this tool that you provide us these things, and we incorporate that into the model. The broader objective here essentially is to have sensors deployed into the ponds, which is undergoing. We have sensors, we'll be deploying sensors into the ponds, and then we'll be training a machine learning model that will identify the optimum values for each of the environmental factors that will affect the growth rate of the shrimp. And then it will give a real-time analysis and prediction for the farmers in hand. Ground survey. So again, we went to the Gujarat coast, Veerawal, where we provided them this application. We took some inputs from them, and so on. So essentially, trying to reach out to the ground level for that. So that is one of the field validation for our work, where the fisher folks and the seaweed cultivators from the Veerawal coast participated. We felt it is important to mention this here. All of this work that we do is incorporates well into the framework of underwater domain awareness that basically brings research and development into the picture of aquatic infrastructure and supports the goal of blue economy, maritime security, marine environment, disaster management, and a whole lot of other things. There's a Wikipedia page on underwater domain awareness. Again, as a responsible researcher, I'm just trying to put that forward. Right. That's all that I have for today. And thank you very much for the opportunity.